My name is Joe Alexandersen and I'm an assistant professor at the University of Southern Denmark. This here is some work Jeffrey Gerard did while he was virtually visiting me as an intern from the University of Montpellier. So this is about geometric exploration and optimization of porous ceramic reactors for bioethanol production. So the motivation for looking at continuous bioreactors are that they have several advantages over batch reactors. And batch reactors are this, and it's mainly due to their smaller size. So you have easier control over the mass and heat transfer, you have smaller temperature and reactant gradients as is illustrated here, and we have a higher safety that follows from that. Porous ceramics have several advantages for bioreactors, and that is that the flow can pass through, and it does that at closely to a uniform rate, as we see here, that a parabolic inlet is sort of spread out as it passes through a porous domain. We can control this rate by sort of varying the porosity, and more importantly, we can seed it with reactants in order to sort of make these continuous porous reactors. However, the porous blocks have a high pressure loss, so we want to see, can we reduce the pressure loss while maintaining good reaction rates. So in order to model the flow through the porous ceramics, we need to know the porosity and permeability. And we find this by looking at the homogenization of a representative volume element. So we see that down here we have pure ceramic here that is only very slightly porous, and then we have these micropores here that we have inserted, and then we can, by applying some pressure gradient, we can catch the flow velocity, and we can compute effective quantities. So our end goal is to 3D print these ceramic structures so that we have the control over these micropores, so we can vary the filament size and these pore sizes. So we see that the pressure drop is the lowest for the thinnest filament and the largest pore size. So that is down up here. So now, sort of looking at the geometry of this, if we reduce the porous part to merely a ceramic circle in the middle here, we see that it basically acts like a solid cylinder. We do get some flow that penetrates, but a lot of it moves around it. By inserting instead, so we still have this ceramic block, we insert a macropore instead, so a fluid circle. We do reduce the pressure drop, and however, it does affect this sort of uniformity. Before we saw that the flow evened out throughout, but this sort of local region accelerates the flow, so we do get this sort of uneven flow here. Overall, we see the less porous material, the lower the pressure drop. But what about the reaction? So this is just purely the flow we're looking. So for bioethanol production, so bioethanol is based on biological sources. So it can be used as a fuel source, which produces significantly less emissions than hydrocarbons. And the common way to sort of produce it, or one of the ways, is to use the yeast, common baker's yeast, to convert glucose, which is then extracted from these biological sources and converting it into ethanol. So it's actually a very complex reaction. There's a lot of individual reaction steps. So we're gonna simplify it quite significantly for our initial purposes. So we have that glucose is converted to ethanol through the activity of the yeast. Even for this simple model, we still need quite a lot of information about the reaction and the diffusion of the various components. And for that, we performed a literature search looking for people who had assumed or even better measured these values, and we also found an old COMSOL application example which actually provided some very nice values that we've also incorporated. So initially we start with a 1D reaction model, and we use the reaction engineering module of COMSOL. This allows for a very quick setup of this 1D model, so that's sort of based on a batch reactor. And then we can easily transfer this to a 2D, 3D model subsequently, which is a really nice feature of the module. So the 1D module shows that we have a very long time scale. So we see here in hundreds of hours. So the amount of yeast X here grows due to consuming some of the glucose, and then it sort of reaches a plateau, and that is when all of the glucose has been eaten, which is around after 125 hours. And therefore the production of ethanol also stagnates. So like I said, we can easily transfer this to a 2D, 3D spatial model. This happens quite automatically. Of course, we still have to define our boundary conditions and various domains. But here we have assumed that the yeast is bound to the ceramic only. Again, we have this ceramic slab and a macro pore in the middle here. And then we look at the first 48 hours where we're pumping glucose-filled solution in, and then we're getting ethanol out at the other side. We do see that this sort of local region here reacts because where the flow is accelerated, we get this plume formation. But again, it reduces the pressure drop. So now we're going to do a geometric exploration using the parametric study feature. We're going to look how the ethanol production and pressure drop vary with the macro pore size and shape. We're going to do that using an ellipse, so we're going to vary the two sizes, so the height and the width. And we see that the production of ethanol is highest for the smallest fluid macro pore, which makes sense. We have more ceramic, more space for the yeast to react with the glucose. The pressure drop similarly is highest at this point, but of course we are interested in the lowest point, which is for the largest fluid macro pore, which again makes sense. But what is more interesting is the production of ethanol per pressure drop. And here we actually see that this is highest for the widest and less tall, so that is the most elliptic one oriented this way. So that's because it produces a very low pressure drop, but doesn't impact the reaction too much. So then we incorporate the optimization module and we do shape optimization of this macro pore. And we see that we start with this elliptic shape we found from the parametric study. We get something like this, a very elongated, very thin fluid macro pore. This increases the ratio of the production to pressure drop. It reduces the pressure drop, increases the ethanol output. We can add additional ellipses and also optimize these, and we get quite significant improvements in the production. So we see here that multiple inclusions of different sizes can give quite a big impact, and that's what we want to use topology optimization for in the future. And with that, I thank you for now, and let me know if you have any questions on my email.